Okay, let us begin. So this one is going to basically cap off all of circular functions by looking at how to solve the application style questions for circular functions. So it's going to be chapter 14 in the Cambridge 1 and 2 book. We'll go through the key kinds of concepts and then we'll have a look at some of the textbook questions. Okay. So the vast majority of what happens with application style questions, at least in the context of circular functions, is that you'll be given some kind of generic circular function to work with, and it'll be your goal to figure out what all of the variables in that circular function are based on the information that you're provided with. There's a whole bunch of ways you could do this. I've given a sort of framework that tells you more or less in order of ease how to get those variables. Like for instance, usually it's pretty easy to solve for n because you just need to figure out what the period of your circular function is, and you can back solve for n. And just a few other steps in order, which is typically when you'll the easiest way to get all these variables. So easier to have a look at an example and see what that actually looks like. This one pulled straight from the book. First things first, based on at least what I'm suggesting here, usually it's pretty okay to figure out what the period is in this situation. So we have a river, and we have this statement here that says the time between high tides is 12 hours. So if you read deeper into this, you basically have a circular function that is depicting the height of the tides with respect to time. So you'll plug in some certain time value and you'll get the height of the tide at that time value. So when we have a statement here that says the time between high tides is 12 hours, that means the period is 12 hours because that's the time in which it takes for the circular function, or in this case the scenario, to repeat once. It goes from high to low and then back to high. So that tells us the period is 12. We also know the period is 2 pi divided by n. And so therefore 12 equals 2 pi divided by n. Rearrange for n, that's going to get us n equals pi over 6. So we've got one term down. We've got this one. Next up, it's usually easy to identify where the vertical translation is. I've called it B simply because that's what the question called it. Usually it's a C. It really doesn't matter. We're just talking about this term here, the vertical translation. In the context of circular functions, the vertical translation is always going to be the mid-level of that circular function, or otherwise known as the average of the circular function. And so when we have this statement that says the average depth of water is 5 meters, if depth is the y values, then that means that the average y value is 5, and for that reason, we can immediately say that our vertical translation is 5. Average meaning the middle value. Next up, now that we have those two terms, we can usually identify the amplitude. You can either do that by doing the difference between the peak and the mid-level, or the trough and the mid-level. Doesn't really matter either which way you do it. In this case, we are told the average is 5 and the high tide depth is 8. So we have the high, we have the peak, we have the middle. The amplitude is thus going to be the difference between those two things. 8 minus 5 gets us a amplitude of 3. Strictly speaking, this could be both positive or negative 3, since it's not really the amplitude, it's just the capital A term that's out the front. Usually you're better off just choosing it to be positive, and then you'll be able to fix it later by choosing when you solve for your horizontal translation, it'll basically fix if you made a quote mistake. You're not actually ever making a mistake by choosing this to be either positive or negative. And to highlight why, basically there's no real information in here that tells us what the, well, said differently, a horizontal translation on a circular function can, if it's picked sufficiently well, can make a translation look like a reflection. So if I were to shift sine x a certain distance, say half a period, it would start looking like cos x. because you're flipping it from being, or sorry, a quarter period actually gets you to cos x. But the point being is that with horizontal translations, you can make it appear like a different circular function. So if you have both that you're trying to solve for, then solving one will allow you to solve the other. And so that's what we do, right? We're choosing positive because why not? Plug everything in. We've got this horizontal translation left to solve. What you'll notice is that there's three unknowns. There's your t, there's your h, and there's your epsilon, the horizontal translation. So if we can knock off the other two, we'll be able to solve for epsilon, because that's the only variable left in the situation. There's this statement in the notes. At noon, there is a high tide. That's told to you here. That statement simply says that at t equals 0, since t is the number of hours after noon, noon must therefore be t equals 0, there is a high tide, where a high tide just means that your depth is 8 meters. And so when you consider what that looks like, you put 8 as your height value, or depth, same thing, they've just used h for depth. 0 is your t value, and then just simplify and solve for epsilon from there. Which means subtract 5 from both sides and divide by 3. You're basically looking for where sine is equal to 1. And the first solution to that would be for epsilon equals pi over 2. So if you choose epsilon equals pi over 2, you'll get a valid choice there. You could choose any version that goes around any number of times around the unit circle. You're better off just choosing the first one, because why go through the effort? Just to further highlight how things can change, we went through symmetry properties at some point. Maybe it was last lesson. I don't remember exactly. But there's this property that when you add a quarter period to sine, it becomes cos. And so if you add this quarter period term, and I say quarter period in the sense of the regular period of 2 pi, basically said if you add pi over 2 to sine, you can knock off that pi over 2 and make it cos, which is why we're able to go from here to here, should you wish to, right? Or should the question require it. All that to say, lots of different circular functions behave the same way. In fact, there's an infinite number of ways you could represent this exact answer. Any questions so far as to how that all works? That is pretty much it. That's the hardest kind of question you'll come across. Everything else is going to be down to your own ability to interpret things. Like being able to look at this and be like, okay, so height, h, is the depth of the tide, and t is time. So being able to interpret what those things mean is going to be basically the most important part of this kind of thing. In fact, we have a very similar circumstance in 14n for the first question. Again, it's a h of t situation, which is talking about sea levels, the tidal heights. First part is just draw a graph, which is whatever. More so, I'll be interested in understanding your ability to interpret these kinds of questions. So I'll just cheat out the graph real quick on the CAS, just so we can have something to point at. But in the meantime, have a think about what's going on in part B, question 1. That's all sketched out now. This is the graph of h of t on the document camera. Part B is asking, when was there a high tide? What does that mean?
Like the max or peak of the graph.
Yeah, exactly right, the peaks of the graph. And the reason why is because the y values represent the height of the tide. And so if you want the high tide, you want the peak on the graph. Absolutely. If you had to do it tech active, it's pretty chill. So you could just go the analyze graph tools and find your maximum. And if you're on the Casio, you would just do a gsolve for max. It's the same thing. So that's telling us one coordinate. We'll get another. And then based on these results, someone tell me what the final answer would therefore be. The big part of this will be in actually wording your answer in a way that makes sense in the context of the application. Like, for example, just saying t equals 3 and t equals 15 isn't going to cut it for these kinds of questions. You have to know what t equals anything actually means in the context of the real world. Or at least insofar as this question.
Chris, do you write 3 a.m. and 3 p.m.?
3 a.m. and 3 p.m. Exactly. Why is that?
Because T is the number of hours after midnight, and like the peaks occur when T is equal to 3 and T is equal to 15. So
Mm-hmm.
just add that after midnight.
Yeah, correct. So 3 hours after midnight is our 3 a.m. and then 15 hours after midnight is the 3 p.m. Yeah, precisely. Part C should also be pretty chill. What was the height of the high tide?
5 meters.
5 meters. Yeah, using the unit becomes important there. So that's how you would do it on CAS. As far as how you would do it tech-free, any thoughts on how you'd actually get those coordinates tech-free?
Wait, Chris, since we know that the height of the high tide should be 5 meters, to like solve it for tech free, would we make h of t is equal to 5 and then solve?
Correct. Yeah. So that's if you hadn't already sketched it yourself. You would set the y value as 5 and then rearrange from there to solve. Yeah, that's correct. In the context of like a fully tech-free thing though, if you're sketching it the way I teach, you would actually already have these coordinates just as you're sketching it, which would be like you do one cycle, so from 0 to 12, you would have the peak, troughs, and mid-levels because you've already just sort of sketched it. But yes, if you didn't already have that sketch, then you would set the y value to be 5, and then rearrange from there. Does anyone need to see what that looks like actually done, or are we fair enough on what you would do?
Chris, can we go through it, please?
Certainly. Maybe not show my passcode. That's better. Okay, so we set the y value to 5, just like you said. 5 equals 5 sine pi over 6t. Who can tell me what you might do to solve this for t?
Are we gonna use a placeholder for pi over 16?
Yeah, you could. That's fair. U equals pi over 6t. 5 equals 5 sine u.
Do we divide both sides by 5 now?
Yep, sounds good. 1 equals sine u. It's probably worth pointing out at this point you want to do it for 0 to 24, but that's a t domain. So t element 0, 24. Okay. What else?
Just can't we? Wouldn't that just mean that u is equal to 0?
U is equal to 0. Yeah. Well, hang on. It's sine of u for 1. It depends on what you mean by u equals 0. Are you saying to sub this in, or are you trying to solve this?
No, I'm just solving that like.
Yeah, okay. So if you're just solving that, sine being the y value means 1 is actually up here.
Oh, so it's pi over 2.
Yeah, pi over 2 is one of them. Yeah. U equals pi over 2. If you remember from our graph, we actually had 2 peaks of it, so that's how you can kind of know. Well, yeah, we wouldn't actually have that if we're doing it fully tech-free. So
5 pi over 2 is the second one.
yeah, 5 pi over 2 is the second one. But I guess one thing worth considering is, how do we know there's going to be a second one? And we'll pretend that we didn't see anything on the CAS because you wouldn't have that. How do you know there's a second one? There is a step we've kind of skipped. So you basically, if you want to do that substitution where you replace the pi over 6t with u, then one thing, the main advantage of doing that is that you get to fix up your domain in terms of u. And so what that means is you sub both of these t values into your u equation, and that allows you to get your domain purely in terms of u, so that when you do all these solutions, you know where to stop. That's if you want to know where to stop. You can absolutely just find a bunch of them and then cut them all down and then see if it fits into 0 to 24. That's perfectly doable as well. But if you do want to see where your end result is, you take these t values, sub them in here. So you sub in 0 into there, that's going to give you the u value of 0. Nice and simple. You sub in 24 into there, you're going to get 24 pi on 6, which is 4 pi. And for that reason, you can now see 0 to 4 pi basically means 2 revolutions around the unit circle, which is why we're going to have 2 peaks rather than just 1. Cool with that? And if so, how do we move on from what we got here? Because that's not quite solved yet.
Do we bring pi over 6t back in?
Correct. Yeah. U was put in there just for our convenience. What we need is to actually have solutions in terms of t. And so yeah, we're just going to put those in. Once we've done that, what do we do from there?
We solve for t?
Yeah, solve for t. Correct. So we can divide everything by pi, cancelling out all that. Multiply everything by 6. That's going to be 6 over 2 is 3. And 30 over 2 is 15. Because 6 5s make 30, and then divide by 2. And so yeah, that's going to give you your t equals 3, t equals 15. We already discussed how that would look as 3 a.m. and 3 p.m. Anything to clarify further from that? If not, have a look at part D, which is asking you what is the height of the tide at 2 a.m. Well, because we've already got the notes out here, we might as well do that one tech-free as well. or at least a little bit of it tech-free. Height of the tide at 2 a.m. So what do we now know from part D? What's the new information there?
Like the height will be a little bit less than 5.
Yeah. Yeah, it'll be a little bit less than 5 because, well, if 5 is the peak, there can only be at one particular time value. So yeah, we would expect it to be less. Sure. But the key information we're told here is 2 a.m. specifically. So what does that actually mean as far as our equation goes? What could we do with that information, 2 a.m.?
Can we sub 2 in
Sure
into
can.
the
Yeah, exactly right. You sub 2 into your equation because you have an equation that says h of t. So if I give it a t value, I get a h value. We want height, we were given time, and so we sub it in. So what we have is some unknown h that we would like to know. And then we have, so it's 5 sine pi on 6t, where t is now 2 because it's 2 a.m. And then we just simplify that down. H equals 5 sine 2 pi on 6 is the same thing as pi on 3. And that gets us to a stage where we need to be familiar with still need to be familiar with the circuit, with the unit circle. Sine of pi over 3. What's that?
Chris, is it root 3 on 2?
Mm-hmm. Yeah, root 3 on 2. Because unit circle, pi over 3 will be that one. It's the next, well, except for 1, it's the next tallest y value, which is why I give it the root 3 on 2. So 5 times root 3 on 2 is, well, best you can do, really. That's as far as that's going to go. If it did say decimal places, it'd be a CAS thing, so you wouldn't have to worry too much about that. Yeah, that's about it there, really. Part E is the exact same question. In fact, if you remember your answers from before here, the t equals 3 and t equals 15, you can actually, without really doing any actual work, you already kind of know what the height of the tide's going to be at 2 p.m. if you look at that. Anyone know off the bat what it's going to be?
It's gonna be the same as 2 a.m.
It's going to be the same, yeah, because it's perfectly cyclical. So if we had a 3 a.m. to 3 p.m. were the two peaks, then 2 a.m. to 2 p.m. are going to be these two y values. Yeah. And so, is this one doable? Yes, it is doable tech-free. Cool. So part F. Boat can only cross the harbour when the tide is at least 2.5 meters above mean sea level. When could the boat cross the harbour? Only allowed to cross if the height of the tide is sufficiently high. Let you digest that for a bit. Think about what's going on there. Maybe some ideas on how I might start.
do we set up a inequality?
Yeah, inequality sounds great to me. How's that going to look?
5 sine pi over 6t is more than or equal to 2.5.
6 is greater than or equal to 2.5. Yes. Yes, that'd be exactly what you do, because you want the tide to be at least 2.5 meters. So if this thing is the tide, then it should be greater than or equal to 2.5. Yeah, precisely. Question now becomes, how do we solve this? It's not too much different. There's a little bit of something we have to consider. I will say, keep in mind that at this stage you would actually have access to the graph of the circular function, so that might be of aid. So the inequality is good. Let's see how much I can get on the same screen. Ha! Yeah, good luck with that. Okay. I guess I'll just say, yeah, consider that you also know the graph. That usually helps a lot with doing inequalities for anything.
Chris, do we bring the 5 over?
Yep, bring the pi over is a good step. So, got sine. Yeah, okay, this is balancing weirdly. Let's try that differently. Sine pi t on 6 greater than or equal to, oh, hang on. Yeah, 2.5 divided by 5, so a half. That's good. So, graphically speaking, we just want to be above that red line. That red line is the line a half. And so if you want to be greater than or equal to a half, you want to be at least either at or above that line. That's what an inequality actually means as far as a graph goes. So when we consider that, it means we don't necessarily need to go through the hell of the algebra around inequalities. We can just rely on this graph and be like, oh, if I just find the breakpoints at where it equals a half, I know just by looking at my graph what domain will have it above and what domain would have it below. So instead of doing this whole inequality, because we have access to the graph, we can just knock it off and just say, yep, equal sign, and then we'll fill in the rest from there. Is it fair enough why we can do that? And if so, let me know how we would continue from here.
Chris, since we don't know the period, can we like use a placeholder in this case?
Another period.
Like we don't really know the exact period of the function.
I mean, you could find it if you wanted it. You could do capital T equals 2 pi divided by n, where n is pi over 6 in this case. So if you want the period, you can get it. But yeah, a placeholder works perfectly fine. I'm just saying you could have either. IT over 6 sine u equals half.
Because when we know this, when we like do this, right, I'm pretty sure that it's gonna be like 1 over 2 at pi over 6, 5 pi over 6,
Mhm.
13 pi over 6, and hold on, 17 pi over 6. So
Yeah,
then
those seem all good.
I think the parts of the graph between it is just what we're looking for. Between the 5 pi over 6 and the second two numbers.
Yeah, that'll be right. Because pi over 6 and 5 pi over 6, whatever those simplify down to, will be these two, and then the other two solutions are going to be these two here and here. So
Yeah,
yes,
except
between those
now we
is,
need to like resubstitute as well.
yeah, correct. So that means we're going to have, whoops, means we're going to have pi t over 6 equals all that. You can very quickly kill the pi's and multiply all the 6's. So that's going to be t equals, well, 1, 5, 13, 17. Yeah, that'll be all your t values. So how do we tie this all up together as far as a nice and neat answer would go?
The boat can cross the harbor from 1 a.m. to 5 a.m. and 1 p.m. to 5 p.m.
Hmm. That's it. 1 a.m., 5 a.m., and then 1 p.m., 5 p.m. Precisely. Yeah. If you wanted to even do a half step there, you could say t is an element of 1 to 5, union 13 to 17. Not required for the answer or anything, more so just so you can at least have something there. If you forget to interpret it in terms of the actual like units, then this will be, I mean, maybe you'll get a nice marker and you'll get some sort of consequential for it. Well, maybe not consequential, but you'll show enough demonstrated understanding to get all but the answer for the mark. Yeah, so that's it. That's one of those. Um, Another question that comes up fairly often is particle motion. In question everything up until 4, apparently. Have a moment to digest what's being asked in question 2. And then, yeah, before we even answer any questions, I'm curious to hear what you guys think of as what that equation is even telling you. And in the meantime, I'll get a sketch going.
Chris, is the answer just 5?
Is the answer 5? Let's see. So,
2A.
yeah. Yeah, that should be
5
right.
meters.
How did you come to that?
Because like okay, so a usual sine graph, its peak is at 1
Hmm.
and y value 1, and then it's amplified by 2, right? That means its peak is now going to be at 2, and then there's a y translation of +3, so that means peak's going to be at 5 now. So
Correct. Yep. So why does the peak of the circular function, like why is the peak the answer in this case?
okay, so its distance from O is given by x meters, right?
Yeah,
And x is equal to that equation. So then the max would be the peak of that function.
correct. Yeah, looking for maximum distance, where distance is on the y-axis, even if it's labeled x, it's a bit weird, but yeah, you'll often find that x is referred to for distances and t for time, which is why you might get weirder axes. But yeah, exactly. If x is your distance, then you want to make this right-hand side as big as it could possibly be. That should make part B a really easy answer from here. What's that going to be?
3 meters.
Ooh, not quite 3 meters. Remember, circular functions go plus and minus from the middle.
Oh wait, sorry, 1. I
Yeah.
started looking at the question in number 3.
Oh, yeah. Okay. Sure.
My bad.
No, you're good. You're good. Oh, yes. Yes, I see. Yeah, those look very similar. In fact, are they just carbon copies of it? Yeah, they basically are. Nice. Yeah. So exact same idea. Mid level of 3, down by 2, gets you to the 1. Nice. A bit harder now. Find the times at which it is 5 meters. I say it's a bit harder. We've technically already done it in the previous question, question 1. What's required here?
We need to make x 5.
Yeah, we need to make x5 precisely. So it's exactly the same thing as what we did when we were solving. If I bring it up on the handwritten, um, so it was this kind of question up here. In fact, we're even setting it to the exact same value, setting it equal to 5. And so you do all this sort of stuff where you do your rearranging, get the circular function on its own. You might do a substitution in here to rearrange in terms of u. And then, yeah, you just get your values from there. Does anyone want to see that worked out for this question? Or are we happy enough with what that would look like? If so, have a think of part E, which is the weirder question. Describe the motion of the particle. Maybe even use this graph here as reference. Can help.
Hey Chris, I'm not sure if this is correct, right? But I remember learning this in like science.
Hmm.
It's like I think the word is like sinusoidal motion.
Okay. Yeah, sinusoidal is what you're looking for. It actually comes from sine and cos, sinusoidal. Yeah, so what you're describing is just what a circular function always has. It has that wave-like pattern. Sinusoidal is correct. What made you think it was called Well, what made you think it was sinusoidal? How would you put that in more plain speak?
So basically the motion of a particle is just like going across like along the line like the line of the function. Like
That's where
let's
it
say
gets
like
dangerous.
on the cas, right? Basically. Like maybe I might have said something wrong, but like from in like my eyes, that's like what I picture, right? So then since that like motion is like sinusoidal,
Mhm.
I just use that word.
Yeah. So you're saying like if my pen's the particle, you reckon it's going like this basically?
Yeah.
That's where it gets a bit dangerous. What is my x-axis? Like we know y-axis is x, is distance. What's my x-axis? I saw you come off mute for a second. I don't think it come through if you said anything.
Oh, it's the time.
Yeah, time. So the issue with saying that it follows this path is that you don't actually see this in time. And so the way to actually describe what the particle's doing would be better on a number line, or at least a kind of number line, which is just if you think about some fixed position, the origin, which does exist in this context, we were told distance from O, origin, um, and we're oscillating between 3 to 5 meters from the origin. So if here's the origin, here's distance 3, here's distance 5, your particle is going back and forth between those two spots. Now, it says it moves on a straight line. That doesn't necessarily mean a horizontal line. It could even be some diagonal line like this. As long as the distance from here to here is 3 and the distance from here to here is 5, it's moving in a straight line back and forth. And so you could describe that as sinusoidal only in the context of what the graph looks like, though. If you were to describe it as what it's actually doing, it's just going back and forth horizontally between a distance of 3 and 5 meters away from some fixed origin. Is it clearer now why that is that? Very easy thing to think. It just sort of follows the line on the graph. Because a lot of things that you do, even like in uni, right? Like you'll literally draw a graph that some object will follow. You'll draw the path of the thing. But we really got to pay attention to what the axes actually are for that. If you want to plot a path for something, both your x and your y have to be distances. Distance in y, distance in x-axis. That way, any line you draw here will genuinely be a path for some particle to follow. Cool. Okay, so that'll set you up for question 3. Literally nothing has changed there. It's even the exact same motion, where in this case it'll be between, what's that, 5, 6, 7, so between 3 and 7 meters away from the origin. It'll go back and forth. Exact same thing. Let's see, question 4. Is there anything actually different there? Particle moves in a vertical. What's a vertical circle? Particle moves in a vertical circle of radius 10. I don't know what a vertical circle is. Hang on a minute. Let me double check the answers here to see. I don't know if that's a typo or not. Can anyone tell me what a vertical circle is? Interesting. Anyway, let's just say it moves along the circumference of a circle, perhaps. The height above the ground is given. Oh, okay. Maybe it's So if you imagine ground. So if I start drawing something, if you imagine ground, then a quote vertical circle would just mean that your circle is like, what would you say, perpendicular to the surface of the ground, whereas what I imagine a horizontal circle would look like would appear flat from this point of view, because the circle is pointing like depth instead of height. So the context of this question, I believe, is going to look like this, which is the particle's moving in some circle. That circle has a radius of 10, and h of t is depicting, like, let's say the particles here. H would be this. The particle was here. H would be that. So we're depicting where it is on this circle with respect to time. That was a weird thing to have to think about there. Is it a bit clearer now why that would be what it is? If so, have a think about, I mean, part A is kind of whatever, but might as well do it anyway, or at least talk about it. Have a think about what part A would be involving us to do.
Chris, we will be subbing in the various numbers into t for the function.
Yeah, absolutely. Find height. If height is a y value, if you sub in t values in there, the only thing left is a y value to solve for. So yeah, that's sorted. Find the period of the motion of the particle. That's also kind of chill. Keyword period is very evocative. There's only one thing that could really mean. What should we do?
Do we do 2 pi divided by pi t over 3? Where
Just pi over 3 though, not the t.
my
But yeah, otherwise that's fine. Yeah, so you would do, my preferred way to go about that would be using an actual division symbol. So you have 2 pi divided by pi over 3, because you're just taking the n value. Then you got 2 pi times 3 over pi. Pi's cancel, period of 6. Now, 6 is not everything. That's just a number. What's the unit on that?
there's still t in the period.
Yeah, so t, it is in time, you're right, yeah, because t for time. But the unit of time specific that we're using is what?
Seconds?
Seconds. Yeah, correct. Time t seconds. So t is in terms of seconds, hence we're going to give the period as 6 seconds rather than any other unit. That's good. Find the greatest height. We've answered that a couple times. Part D. Find the first 4 times the particle's at a specific height. Yeah, I mean, we've already answered stuff of C, D, and E. Is there anything else to actually have a look at then? Temperature at midnight. Max, min, specific. Like, you start to see that kind of repeat. So if you have a look back at the PDF, like greatest height of particle, well, you just look, what's the greatest height going to be? Middle value of 10, amplitude of 10, it's going to be 20. First 4 times a particle is at a height of 15 meters. You're told meters, you want time, so you plug in the meters and you solve for t. Same thing there. What is temperature at midnight? Temperature is the y value, midnight is a time value. So you plug in what you know and you solve for what you don't know. So you can see a lot of these are repetitive. Max min, right? What's the maximum based on this? What's the minimum based on this? What time's warmer than 20? That implies an inequality. So you'd use a graph. I'll see if there's anything actually unique there. Maybe this. Boats need a depth of W meters are permitted only if the depth of the water is at least W meters for a continuous period of 1 hour. Okay, I mean that's slightly different. Yeah, we can do 6c. Just keep in mind you would need this equation for it. Yeah, have a read of 6c, try to absorb the context there, and then I'll also get a picture up on the CAS. Okay, we have a picture for question 6. Does anyone got an idea? Yeah, you're about to say?
So you know like where the peak is, right, of the function?
Uh-huh.
I was thinking that like I know like it's not maybe like mathematically speaking correct, but you know so there's T is like 1 hour and the peak is like a point of time during the hour. So if we look half an hour to the negative side of that peak and then half an hour to the positive side of the peak, would we get the I think that's like where the largest value of W would be.
Yeah, that's a perfectly mathematically suitable way of doing that. There's nothing wrong about that. Yeah, because you need to guarantee a continuous period of 1 hour, and so the best possible chance you'd have of achieving that is like, okay, let's start with the biggest thing and then work our way down there. Because if that can't achieve it, then nothing will. So yeah, that's beautifully done. Yeah.
Yeah, because my process of thinking was it has to be symmetrical, right? Because it's like W there's only one W value,
Yeah.
whereas like we're looking at 2 points on the graph.
Yeah. Yeah. So like literally wherever you put W, like let's say I put W at, well, we can say it's at 10, right? It doesn't even matter where I put it. If you need to guarantee an hour, then you would start here and work your way back until this distance here was 1, because t is in, well, actually, is t in hours? Yeah, it is. And so yeah, you work your way back from that, which is what you've suggested, which is start by finding this peak. So we'll grab that peak, which is at t equals 3. And so if you go half an hour either side, it would be whatever the y value is at 3.5 or 2.5. So if we go back, oh, maybe not there, we do our 3.5, that's going to get us some height. Reminder that we are allowed to do it to the decimal places, correct to 1 decimal place. And so if we literally take a copy of this, put it on our graph, what did I just do? Why did that happen? F of 3.5. That's weird. F2x 3 sine plus 10. Yeah. We found a maximum at 3. What's 3 get me? Oh, it's just that close. Oh, okay. Sure. So if I zoom in real close, we can say like fact, yeah, a good one would be from 2.5 to 3.5. Let me change our y values accordingly. So 13 was a max. So we put 13 in the max spot. 12.5, let's say, why not? And then, yeah, like you can see how that now cuts perfectly at that 1 hour distance, because if you look for what I've set for the window settings, well, it's gone to fractions, but 2.5 to 3.5 is the distance of 1. So that was more so just my window settings made it look weird than anything else. So yeah, it was totally valid to do it that way. And so for the actual answer that we give, how do we actually depict this as a final answer?
Did we just say 12.9 meters?
12.9 meters. Let's see. Correct one is place. Largest value of W. Yeah, W equals 12.9 meters. Yeah, that sounds good to me. Yeah, nothing else you'd have to say there, really. Give the value, give the unit, give W. Yeah, easy. Okay, that's that. They give you one here that's in degrees, weirdly enough, if you look at the PDF. Just be sure that as soon as you see that degree symbol in there, this actually caught us out. I don't remember what class I was running. Actually, no, I think it was one of my. Yeah, I know who it was. The degree or radians mode on your CAS is different depending on if you're on a graphing tool or on the calculator tool. If you toggle between degrees and radians on this, it does not toggle degrees and radians on the calculator tool, and vice versa. Now, you guys can actually click that button, I can't. But all that to say, basically, if you're going through and doing your document settings and selecting degrees or radians, or even just clicking that button, it does not carry over. And I had a student who toggled it so many times, but didn't realize that it wasn't actually changing the graph. And for this one, if you want to actually plot that thing, well, you're going to want it in degrees, because it's in, well, it's got that degree symbol in it. So just keep that one in mind. They have a unique between the two graphing tool and the calculator tool. But otherwise, yeah, I don't think there's anything else too crazy in question 7. I'll sort of just talk over it for the remaining couple of minutes. So again, it's another depth of water thing. They're really not that inventive with these questions, huh? It's more depth. We got a fully unknown circular function. High tide depth of 7, low tide is 3 meters. Show that R equals 30. Well, if R is on this, then that's basically, you care about the period in that case. So period 2 pi divided by n, you now have to figure out what the period would be. Now, worth pointing out, you're given some time duration. This is not actually the period though, because it's going from high to low. You don't want to go from high to low. You want to go from high to low and then back to high. So the period in this case would actually be 12 hours rather than 6 hours. So you set 12 equals 2 pi over n, rearrange, but you, there you go, but you can't use pi, you use 180. Is that how that one works? Let's find out, because it's in degrees. If I go to the handwritten bit, we do 12 equals 2 times pi over n. 12 equals, well, let's say 12n equals 360. N equals 360 on 12. 12 fits into 36 3 times, and then 10 more, so 30. Yeah, okay. So that's the trick there, using 180 instead of pi for the period calculation. Cheeky one. I've used n. Obviously, the questions used r. Just whatever. You would obviously use r for that. I just kind of defaulted to what I knew. So if I need to clarify that, feel free to stay behind for a bit. Otherwise, enjoy the rest of your day.